And it was at a time of great creativity.
As the Islamic Empire spread from the Middle East to India, North
reached where it did without the contributions of these people.
Modern engineers like Professor Al-Hassani of Manchester University in England are now studying ingenious machines like the tea-serving girl and are astonished by the masterly use of technologies that we still employ today.
The tea-serving girl principally is a tank on top of a robot. This tank has a hole that allows the water or the drink or the tea to come out of it.
By using a tank that regulates the flow of liquid, the machine builders were able to astonish and amuse their contemporaries. A reservoir is filled with liquid which drips at a constant rate into a bucket. When the liquid reaches a certain level, timed precisely to 7.5 minutes, it empties into the glass in the servant girl's hand. The weight of the glass triggers a mechanism that causes the servant girl to roll down a slope, opening the door and presenting the drink to the guests. This kind of trick device would have further enhanced the mystery and genius that surrounded the engineers of the time.
The use of the crank and connecting it to what we call a camshaft, this had revolutionized machinery and engines like the steam engines and the diesel engines and the petrol engines.
This simple mechanical component allows the conversion of continuous rotary motion into a reciprocating one. Hand-operated cranks had been known for centuries, but the incorporation of a crank-connecting rod system in a rotating machine was an incredible innovation. Modern engineers who have studied Al-Jazari's design have discovered that the horizontal axle of the machine is turned by gears and that the end of the crank slides in the hinged connecting rod, causing it to oscillate around its hinge and thus causing the water bucket to rise and fall. Until modern scholars decoded Al-Jazari's design, it was believed that this system was an invention of 15th century Europe, but remarkably, Al-Jazari was using this crank device in his machine 2 centuries earlier.
Take Jazari's machine number 5. It is actually a double-acting suction pump. It has got 2 cylinders with pistons reciprocating to the right and to the left.
The pump is driven by a water wheel, which drives through a system of gears an oscillating slot rod, to which the rods of the 2 pistons are attached. The pistons work in horizontally opposed cylinders, each provided with valve-operated suction and delivery pipes. The delivery pipes are joined above the center of the machine to form a single outlet into the irrigation system. Al-Jazari's amazing developments in the construction of water-moving machines soon led to other Eastern inventors and scientists taking the tradition further and building even more amazing devices. While Europe lagged behind in the building of complex machines during this period, engineering in the East was becoming even more advanced than we have previously thought.
The science of mechanics was generally known as the science of tricks, because what one is doing, one is using mechanical phenomena to actually achieve what could have been impossible to achieve.
The key was a highly sophisticated application of hydraulic technology. By controlling air and water pressure, the ancients were able to automatically regulate their machines. The precise engineering techniques employed in this Banu Musa trick device would lay many of the foundations for modern mechanics.
This typical machine is effectively to give you an intermittent spouts of water or a drink. It uses very cleverly 2 new systems which were introduced in the early 9th century.
The first system is a ground conical valve, which is used to regulate the flow of water.
When the water is in the top tank, it will go through a hole in the bottom of the tank, like it is now doing there. In that hole, there is a conical ground valve that if it goes up, it would shut the hole.
The second is a feedback mechanism that controls the timing of the movement of the valve.
Because there is a siphon system in the middle tank, it will suck the water back into a smaller tank below. Now the third lower tank has a float. If the float goes up, then water will gush out. However, because it goes up, it will push that seating valve because it's connected with the seating valve, and then it will stop the water coming down from the top tank.
This device, and others like it, demonstrate an amazing knowledge of the use of differential pressures. Exactly the same techniques are used to control mechanisms in everything from washing machines to jet engines today.
We have seen an emergence of a civilization which has influenced our present-day civilization enormously in our homes, in our hospitals, in our schools. And even when you look up the sky, a lot of the stars are still named by Arabic names.
But how does this complex and awe-inspiring device actually work? And how did Al-Jazari improve so fundamentally on the timing devices of his ancient forefathers? Amazingly, the elephant clock consists of several mechanisms that match those used in modern engineering. Inside the belly of the elephant is a submersible float with a small hole which is carefully calibrated to produce a specific flow of water which determines the rate at which the float sinks, and therefore the time at which the clock strikes. The sinking activates a tripping mechanism, which sets a series of events in motion that mark the passage of time and strike the hour. At this point, the float is tilted out of the water, emptying its contents. It will then rest on the water's surface, and the cycle is repeated. The clock employs automata, such as the striking of a cymbal and the chirping of a bird to mark the passage of the hours.
For its time, it is a very complicated clock in the sense that it has automatic feedback, and this continues almost like a perpetual motion machine.
The elephant clock is one of the finest examples